gold and mercury to us look quite different. Like gold's like a chunky kind of metal, and mercury, which is sometimes called quicksilver, mercury is a liquid. All right, it's kind of fun to look at, but it's also very dangerous, so be careful. On the other hand, those things that are rotating there, those are the ways that gold and mercury are related on the atomic level. And you can see they look very similar. So chemists are always interested in the nature of matter and how it relates to the atoms and the molecules. And on this example, the atomic level looks quite similar, but in the real world, the pictures on the upper left, the atoms look a lot different. The elements look a lot different. As a chemist, you have to be thinking about what I call the macroscopic world, and that's the world we use to interpret through our eyes, all right? Gold looks different than mercury, all right? No problem. Water looks different than table salt, absolutely, all right? However, as a chemist, we're going to think about things on the atomic level as well, and that's what those rotating things are for gold and mercury, and we'll talk about those in Chem 222. But on the atomic level, they look very similar. On the macroscopic world, gold and mercury look quite different, and we can use symbols, i.e. those element symbols and stuff like that, to represent these things to each other, so we can talk about them and figure out what's going on, stuff like that.
A balloon filled with hydrogen and surrounded by air represents a potential chemical reaction. To initiate the reaction, we need to ignite the balloon. The hydrogen will combine with oxygen in the air to form water in gaseous form, releasing considerable energy in the process. At the molecular scale, the molecules of gaseous hydrogen, H2, and oxygen, O2, combine to produce H2O, water, generating heat and light.
So in this video, you actually got to see a balloon filled with hydrogen gas basically burned, all right? And the burning is just there to add some oxygen. And it adds oxygen to the hydrogen to make water. And there's a lot of energy released, all right? The balloon went boom. Sound effects not necessary, all right? Anyway, so in the macroscopic world, you light a balloon filled with hydrogen, makes a bam. Okay, cool. On the atomic level, all right, the hydrogen, which are the little white molecules there together. They're represented by those pieces right here and right there and right there. Those are H2 molecules, or hydrogen, all right? And the oxygen, which is around us all the time, is represented by those two little red atom kind of combinations floating around. And basically the match, the light, just like starts the party, and at the end of the day then, it makes water, H2O. So you can see that water, H2O, would have two white hydrogens and one red oxygen. And we'll talk more about this formation here pretty soon. But on the atomic level, that's what's happening. The H2 in the balloon reacts with the O2 on the outside of the balloon to make water at the end, the H2O molecules that you see. Now, that took a lot of words, and chemists can be very lazy. So it's also nice to think about it from a symbolic perspective, i.e., how can we write this? And that's what this thing is right here. This is a balanced chemical reaction, and we'll talk about this later on in Chem 221. But what it's saying is that you're taking two of those red H2s, and it's a gas, plus one of the O2s, the red ones that are to gas too, and you're going to make two waters, two H2O. And this is gaseous water. The G stands for gas. All right, you could, if you cooled it down, have liquid water or something like that, but right now it's gas. So all of these perspectives, super important when it comes to chemistry. This leads us more into what solids, liquids, and gases are all about. And this is a really interesting part of chemistry as well. All substances, arguably, can have solid, liquid, and gas phases. Solids have very rigid shapes. They're very fixed volumes. And chemists understand solids pretty well. And you are around solids all the time. Table salt or sugar, table sugar are great examples of this. There are also things like, iron and things like that are around. Solids are really good, but you can't really pour a solid. The volume is fixed, all right? So solids have some uses for them, but also some weirdness too. Now, a liquid, on the other hand, you can pour. It doesn't have a fixed shape, all right? It will fill a container completely. Like if you pour solid into a container, you'll have like little places where it kind of makes little holes and stuff like that. Liquids don't have that. Liquids are really important, of course, water being the most important of all of them, but liquids are arguably not well understood. It's very hard to predict something that's so dynamic and moves around all the time. Gases, on the other hand, are another phase of matter. They will expand to fill their container, and if you give them enough time, they'll be consistent about it. Gases is actually where chemistry started, and chemists have a very good understanding of how gases work. We'll talk more about this in Chem 222 when we talk about gases, but it's amazing that gases, which are so hard to control, are actually pretty well understood. Now, just to be fair, there is a fourth and very important phase of matter called plasma. And plasma in the universe is the most important. But in the Earth, in our world of day-to-day kind of things, solids, liquids, and gases dominate. So we won't talk about plasma until Chem 222, but just keep that in the back of your mind, man. These things can be pretty cool.
According to the kinetic molecular theory, the molecules of a solid are locked in place, though they have motion. Molecules of a liquid are closely associated with each other, but move relative to one another. Molecules of a gas move independently and occupy a much larger volume than those of a corresponding liquid or solid.
The kinetic nature of matter comes from what's called the kinetic molecular theory, and the KMT for short, which is what I use because I don't want to use a lot of syllables. But anyway, the KMT is the way that chemists think about it. So you can see that each of those solid, liquid, gas boxes there, they have some kind of atom or molecule, doesn't matter, but that's what they are. In the solid phase then, those molecules are pretty tight together. They're held pretty tightly together. But if you add a little bit of energy, you can arguably turn them into a liquid where there still is consistency between the molecules, but it's not as strong as solids. Like liquids will flow, solids don't usually flow. On the other hand, you add even more energy, gases have no interaction with each other at all. They're almost like independent little entities. So the gases and stuff, you have to have something contain them or else it's really crazy. We'll talk about the KMT with phases of matter as we go through this course, but I'm introducing it now just to let you know that's what chemists use right now anyway as the idea of how solids are different than liquids and liquids are different from gases. You have to know how to turn one phase of matter into the other. So the energy of transitions is really important to scientists. And I have down there the three phases. The lower left is solid or ice, or in this case looks like snow more than ice. The lower right is a liquid water, all right, so you can see the liquid on it. And the upper right, the steam over the lake, that's like gaseous water. All of them are water. They're all H2O. But the question is, how do you go from solid to liquid or liquid to gas? Anytime you go from solid to liquid or liquid to gas, it's going to take energy to make those transitions possible. They don't just happen by themselves. And chemists refer to this as an endothermic transition. So endothermic means that it takes energy to happen. So solids to liquids, liquids to gas, always endothermic. On the other hand, if you go gas to liquid or liquid to solid, you're going to see that you actually end up releasing energy. And if you release energy, chemists call that kind of transformation exothermic. So this slide right here is basically introducing the terms endothermic and exothermic. Endothermic means it takes energy to happen. Exothermic means you're going to get energy out to make it happen. Now, in the middle part right here, you can see there's like a solid, there's a liquid, and there's a gas line. I guess I said solid first, but you get the idea, all right? Anyway, blah, blah, blah. Anyway, this is an energy axis, all right? So you can see that going from a solid to a gas, which is this first arrow right here, which is called sublimation, by the way, that's endothermic. It's going to take energy. The higher state is a higher energy than the lower, so you're going to have to add energy to make it happen. On the other hand, if you go from the gas to the liquid through the process of condensation, the energy goes down. Those are going to be exothermic. The lower state, the final state is lower in energy than the initial state, so energy was released. Also, freezing is the same thing. You're going from higher liquid energy to a lower solid energy. These will be important to us later on, but really for right now, what I want you to just hear is endo and exothermic. And endothermic means it needs energy to happen. Exothermic means you're going to get energy out when it happens. Physical properties are important when you want to identify a compound that you may not be totally sure what it is. And a physical property is pretty cool. It's a type of measurement that doesn't change the substance itself. So for example, if you look at that bromine right there, it's kind of a brown-red color. That's the color, all right? And looking at the color doesn't change the fact that it's bromine, all right? If you wanted to know more about bromine, you could take a melting point or a boiling point, which is something a chemist can do, but you're not going to destroy the sample. You could still use it. Also, the odor of chemicals sometimes is considered a physical property because odor is something that you could really redo. Physical changes, then, are things that are related to the physical property. So if you boil that liquid, that's a boiling point measurement, by the way, that would be a physical change. You could melt a solid, all right? Solid to liquid would be a physical change. You can also take a solid and put it in a liquid. And if it makes a mixture, what's called a homogeneous mixture, which just means one phase, it doesn't look like a rock in the water, it looks like it's just one thing, that makes a solution. And a solution is a physical change. We'll talk about these later too, but a physical property is a way that chemists can figure out what a compound is without destroying the compound itself. And believe it or not, that's kind of useful sometimes. Which of the following is not a physical change? Now remember, physical change, it's reversible, all right? So freezing of a liquid to form a solid, I think we could take that solid and make it a liquid again. So that should be something that's reversible. I think that's going to be a physical change, all right? We can redo it if we want to. B, it says dissolving a solid in water form a solution. That was that last little blurb there at the end. In theory, if you took a solid like sodium chloride, table salt, and put it in water, you could evaporate the water to get the table salt back again. So that is also reversible. So that's not a problem. That is a physical change that doesn't count here. The next one, evaporating liquid water into steam. Well, we could take that steam and collect it, turn it back into liquid water. That's reversible. That's no problem. So that wouldn't qualify here. However, the next one, if you take a piece of paper and you burn it, all right, that's kind of fun to do. But if you think, oops, I needed that paper back, it's, I would argue, impossible or pretty gosh darn close to impossible to get that ash back to the original place that the piece of paper was. So that is not a reversible process. D is definitely not a physical change, all right? We can't reverse it. The last one, if you take ice, solid water, and turn it to vapor, like gaseous water, yeah, you can reverse that one. But there's no way that you're going to take ash and turn it back to your original piece of paper. That's going to be, we're going to see here, a chemical change where you have actually transformations at the chemical level happening. Speaking of chemical change, physical properties are really cool because they can help you identify compounds, but physical things are reversible and they're really important. But sometimes you need chemical changes too, the way that chemicals react with one or another. But just realize that if you do one of these, it's going to be really difficult to get it back to the original form, hence the burning of paper earlier. Physical properties, again, don't change the composition. Chemical properties do. So in the upper one, you've got a little magnet there attracting paper clips. All right, that's a physical property. All right, you can get the paper clip off, no problem. On the other hand, poor Coyote down there, after being with a Roadrunner, his TNT goes off. I'm amazed he's still there. But anyway, that's obviously a chemical property. All right, you can't take the TNT and get it back to TNT after you've exploded it. It would be all gone stuff. Terrible. Terrible.